Good morning one and all. Today I am discussing about Applied Geotechnical Engineering 18 Series 6.2 for 6th semester students, Module 2, Lecture Class 2. Today we are discussing about stresses in soil in general. In particular, we are discussing about concentrated load, circular load, rectangular load, equivalent point load, etc. Yeah, this is sigma z, stress distribution at a depth z for line load. Line load means your compound load is a line load. We are having a considerable length compared to a cross-sectional dimension. So, which is given by formula sigma z is equal to 2q divided by pi z divided by 1 plus r by z whole square to the power of 2, where q is quantity of load in kilonewton per meter. Next one is sigma z for strip footing. Uniform strip load such as load on a long wall footing of sufficient width, where let us consider B is the width of the footing on considerable length L. We want to find out at the sigma z at depth Z at the middle of the footing B by 2 at a radius, the angle of that particular B by 2 from the edge is Q by 2, then sigma z is equal to Q pi into that is Q into pi into theta plus sine theta. So we can use this equation to calculate that value, where theta is in kilonewton per meter square. Suppose if it is, I think, at the one of the corner away from the loaded area, then the sigma z value is calculated by sigma z is equal to Q by pi into B is width of the footing plus sine beta. Beta is the angle made by the two extremities of the footing into cos beta plus 2 times delta. So delta is the extreme end of the footing line from the point of application P. So where Q is kilonewton per meter square. Next, coming to the sigma z for circular footing load. Let us consider a circular footing having a radius A. Then the uniformly distributed load will be Q, and Z is the depth at which the stress is to be calculated. Then sigma Z is the stress at that particular point, which is given by sigma Z is equal to Q into 1 minus 1 divided by 1 plus A by Z whole square to the power 3 by 2. So principle of superposition. The principle of superposition may be used to compute the stresses beneath any point inside or outside a uniformly loaded rectangular area. Two cases there. Case 1, sigma z within the loaded area, and second case 2, when a sigma z is outside the loaded area. So first let us consider a rectangular footing A, B, C, D, and we want to find out the stress at point O, which is inside the loaded area. In order to find out the stress inside the loaded area, let us divide that entire footing into 4 parts. That means wherever O is there, draw a line parallel to longitudinal axis and perpendicular to longitudinal axis. So now 4 components has been divided as 1, 2, 3, 4. So now, as per principle of superposition, sigma z is equal to Q into I. I is Boson's influence factor, where I is equal to I due to first component, stress from this component at this point, stress of this component from this point, stress of this component from CG of this point, stress of for this area from CG of this point. If you calculate it, that is sigma z is Q into I, that is equal to Q into I1 plus I2 plus I3 plus I4, where I is the Boson's influence factor. Next, suppose if I want to calculate stress away from the loaded area, suppose when we constructed some, when a footing is already existing in the neighbor site, but in the adjacent site we want to make some underground excavation for basement construction, whether that footing will have any influence on our excavation site, we have to calculate. This is the neighbor site, this is our site. Okay, we have to calculate it. How to calculate it? Transfer this image on a drawing sheet. ABCD is the loaded area on which the existing load intensity will be Q. Suppose this is the O is the point at which we have to calculate what is the effect of this load stress at this point. So O is equal to, we have to make a rectangle. So that is OB1 CD1 as a one rectangle where, so the area O, the area ABCD, the area ABCD is equal to B1C D1, B1C D1 O, B1C D1 O ABCD is equal to, the area ABCD is equal to ABCD B1C D1O, this entire area, minus OB1 BD2, this area we have to deduct it, minus OA1 D1, this area we have to deduct it. 2 times we are deducted this component when we are deducting this area and this area, therefore we have to add this area. So OA1 AD2. So now the equation sigma z will be Q into OB1 CD1 stress at this point from here is I1 minus OB1 BD2. So mid-ordinate is this, if you calculate, that is I2 OA1 D1 for this one from this point I3, OA1 AD2 is I4. So this is the principle of what is called as superposition. So the principle of superposition may be used to compute the stress beneath any point inside our loaded area and outside the loaded rectangular area. Now coming to the MCQ question, sigma z for line load. The load on a narrow long wall footing of a small width is given by Q is equal to kilonewton per meter. So that is the Q value, it is not the entire equation, therefore it is false. Sigma z of line load on a narrow long wall footing of small width sigma z is given by true. That equation, sigma z as strip footing uniform strip load such as load on a long wall footing of sufficient width, the equation is given, it is true. Sigma z for strip footing, so the equation is given true. Sigma z for circular footing and loaded area, the equation is given, that is also true. Principle of superposition, Q divided by, that is, it is false. The principle of superposition used to compute the stress beneath any point inside or outside loaded area, that is true. The principle here compute the stress beneath any point outside or inside a loaded rectangular area. So this is seventh one is circular, they are given, therefore is false. The rectangular is given, eighth one it is true. The principle of superposition is used to compute the stress beneath any point inside or outside uniform loaded square area. This is also false. Sigma z for strip footing is given, this is equation, it should be plus, therefore it is also false. So these are the references that we are used to prepare this material. I take this opportunity to thank Department of Collegiate and Technical Education officers and students for giving me an opportunity to deliver this particular lecture on applied geotechnical engineering. Thank you, one and all.